Hi everybody, in this video I want to do an example that involves the magnetic force, the gravitational force, and Newton's second law all together. Alright, so here's the situation. First, let's take care of our directions. Imagine that the direction north is into the page, south would therefore be out of the page or out of the board, east would then be to the right, and west would be to the left. Toward the top of the board will be up, like away from the ground, and down toward the bottom of the board will be down toward the ground. All right, so north, south, east, west, up, and down. All right, so in this problem, and I'm going to take x to be in the east direction, y to be in the up direction. That would mean z, by our right-hand rule, would be south. Okay, so here's the physical problem. We have a magnetic field of magnitude 10 Tesla and direction west, which means it's in the negative x direction. We have a charged particle that has a speed of 5,000 meters per second. The direction of its velocity is south, so that'd be coming out of the board. So overall, the velocity is 5,000 meters per second south. We don't know the mass of this charged particle. We know something about its charge. We don't know the sign of it, but let's say we're given that the absolute value of the charge is 50 microcoulombs, where micro is 10 to the minus sixth. All right. The last thing we're given is information about the acceleration of this charged particle. We're told that at this instant, the acceleration is 7 meters per second downward. That would be in the negative y direction. Okay. So given all this information, let's try to figure out what the problem is asking us to solve. We're supposed to find the mass, and we're supposed to determine the sign of the charge. All right, so let's start by drawing a free body diagram. Because we've got acceleration, we've got forces, maybe we can use a free body diagram and Newton's second law to put all this together. All right, so we have a downward gravitational force of magnitude mg. Now we got to put in the magnetic force. Now we might guess, given this information, the magnetic force has to be either up or down because the acceleration is along the negative y direction. This force is in the negative y direction. We have no other forces in the x direction. So if the magnetic force had an x component somehow, there'd have to be some other third force in there that we'd have to have in there to cancel that out. So just because of the way this is going, it looks like we're going to have something that's either in the positive y direction or the negative y direction with regard to the magnetic force. Let's figure out those possibilities. So I'm not done with the free body diagram. We'll put the magnetic force in there in just a moment. But let's work out the direction of the magnetic force. Q V cross B. Okay, so this is the expression for the magnetic force. Let's work out the direction of V cross B. So, V vector, that's the direction of the charged particle's velocity. It's out of the board. B, that's the direction of the magnetic field. So I need to curl my fingers from the velocity into the direction of the magnetic field. I need to curl my fingers from that direction to that direction. So here we go. V cross B. My thumb will point in the direction of V cross B. That's clearly in the negative y direction. Or I'll just say down. All right, so here's what we have, our options for the magnetic force. If the charge is positive, then I'd have positive times down. That'd give me a direction of down for the magnetic force. If the charge is negative, I have the negative of down, which would give me up. All right, so now let's look at our acceleration information. If we had no magnetic force at all and just this gravitational force, the acceleration would be 9.8 meters per second downward. But instead, it's 7. So without a magnetic force, we'd have 9.8 meters per second, but we have less than that, so we must have some force upward. That's the magnetic force. So we can infer that the magnetic force must be upward. I'll just represent the magnitude, force, magnitude of that, arrow giving the direction. All right. So if this is up, to have an equality there, I need to have a negative charge. So we've already got the sign of the charge. The sign of the charge is negative. Okay, so now what I'm going to do, since here's my free body diagram, the only stuff that's interesting is in the y direction. I'm going to apply Newton's second law in component form in the y direction. But first, I'm going to erase this. So let's apply Newton's second law in the y direction. Sum of the forces acting in the y direction on the mass equals the mass times acceleration in the y direction. Our forces, we've got F sub m in the positive y direction and mg in the negative y direction equals ma sub y. All right, let's figure out F sub m. I'm going to write that here temporarily and then erase it. F sub m, that's going to be, we've got Q V cross B. Now if I want to get the magnitude of that, F sub m, I take the absolute value of the leading scalar, and I have to take the magnitude of V cross B. That'll be magnitude of the first vector, magnitude of the second vector, sine of the angle between them. Let's figure out that angle. The velocity of this charged particle is coming out of the page. The magnetic field is to the left. There's a 90-degree angle there between this and this. So we have sine of 90 degrees. Sine of 90 degrees is 1. And so the magnitude of the magnetic force will just be absolute value Q VB in this case. All right, so I'm going to erase this just so I have some room. Boom. So for the magnetic force, we had absolute value Q, magnitude of the velocity, magnitude of the magnetic field. We got minus mg equals m a sub y. All right, so my job here now is just to solve for the mass. So I'll do that in a couple steps. All right, so I can plug in for all these quantities. I'm just going to write all the quantities down. All right, so if you plug all of these in, the charge is 50 times 10 to the minus 6 coulombs. That's the absolute value of that. Velocity of magnitude of 5,000 meters per second. Magnitude of magnetic field is 10 Tesla. G is a positive 9.8 meters per second per second. Remember, G is the magnitude of the free fall acceleration. And A sub y, this is a y component, is 7 meters per second, downward, so negative for the negative y direction. So I'd have 9.8 plus a negative 7 meters per second. That's going to give me a positive 2.8 meters per second here, and all these other things are positive. The mass, it comes out as, I'll write the answer, if you plug all those things in, 0.892 kilograms.